Thank you very much. I want to say not only is it wonderful that the RI is back open, that this is also the first public talk I've managed to do since 2019, so it's wonderful for me as well. And we're looking tonight at patterns, and specifically patterns that help us understand and explain what goes on in the universe. Specifically, the 10 that I've picked out are listed here, and I'm just going to highlight some of them. Now, I have to confess, I'm actually only going to talk about 6 of them in any great detail. The book this is based on has 10 in, but if I'd gone through all 10, you would have very tiny little bits on each one. I wanted to have a little bit more time on each one. So if you really want to go to the Royal Institution afterwards and ask for 40% of your admission fee back, you can look for a negotiation, but I hope you won't decide that's a good idea. So the 10 I'll be covering, the ones I'll be speaking about tonight are the ones in yellow. But before we actually look at those patterns, I think there's 2 things we need to think about. One's science. This is the Royal Institution, so we ought to be thinking about science. And all the patterns in this book, all the patterns I'll be talking about tonight, are patterns involved in science. Now, according to my dictionary, this is my dictionary definition of science, it's the systematic study of the structure and behaviour of the physical and natural world through observation and experiment. And I think you can go as far as to say, if there were not patterns, there would not be science. If, for instance, every time you go and measure something, it's different. Every time you look at the night sky, it's totally different. Everything you do, it's totally different. It's chaos. There is no pattern. There can be no science. There can be no explanation. Science is built on patterns. Now, when they sort of put me on hold before I came in here, they rather dangerously put me in the Royal Institution Library, which is a wonderful selection of books, and I was browsing through it and actually found a fascinating book called Puzzles, Problems and Enigmas by John Simon, who was a physicist at Bristol University. And he makes a really nice little comment. He says, "Science is to be believed because it can be openly criticised. The criterion for belief is not authority nor logical necessity, but nobody has yet found a more convincing pattern of interpretation. Science is all about finding the most convincing pattern of interpretation for what we observe and discover in experiments." So, he's said this for me, really. There are many patterns in science, thousands of patterns in science that I could have covered. And whenever you, if you like, produce a list of things, inevitably people say, "Why didn't you talk about this pattern? Why didn't you talk about this?" or whatever. These are not, I'm not claiming these are the best ever, 10 best ever science patterns as you might get in a Channel 4 TV program. I'm not even going to say they're the most important patterns in science. They're 10 that I find really interesting myself, and I hope in sharing some of those with you, you'll find them interesting too. So I think hopefully you're all happy with the concept that patterns are important to science. But I guess there's one lower level issue here. What is a pattern in the first place? What are patterns? The fact is patterns are essential, not just in science, but for our interaction with the world around us. If we had to learn how to operate every single light switch individually, we would never get on in life. But luckily, there's a broad pattern. I know if I put my finger on the light switch and press down, I will turn the light on, unless I'm in America and I discovered they put the light switches on the wall upside down. But that's apart. I know the pattern of light switches. I know how to switch the light on. I don't have to learn it every time. Those patterns are crucial. And obviously, historically, and even in an evolutionary sense, patterns have been with us for a long way because they are about survival. We look for patterns naturally. You look for the pattern of a predator in the bushes. Is that a tiger out there coming to get me? You look for the pattern of food if you're searching for food, if you're foraging. And we are particularly good at recognizing the pattern of human faces. Faces are incredibly important patterns to us and obviously important to the survival of the species. So much so that we're actually really good at fooling ourselves. We're very good at, for instance, seeing patterns that just aren't there. This is a classic example, photograph some of you may have seen in the past. It's a photograph of the surface of Mars. And when it came out, some of the less reputable newspapers got all excited about the face on Mars. If you look in the object in the sort of top left-hand corner, you can see it's clearly a sculpture of a face that somebody has carved on Mars. Amazing. This is a phenomenon that has a rather fancy name there that I probably can't pronounce because I didn't do Greek at school, something like pareidolia. It is the fact that we actually are so good at recognizing the pattern of faces, we see that pattern even when it's not there. As it happens, if you look at a better picture of it, this was the best one that was around at the time, now we have a much better picture of that same structure. The face pretty much disappears. You can just about see where it was, but it clearly isn't a carving of a face. So patterns can mislead us because we see them when they aren't there, but equally, there can be a pattern we see, it's a real pattern, but we misinterpret it. And remember what Feynman said in that book, science is basically about getting the best pattern. We have to move on sometimes from our current patterns. And one of the ways a pattern can very easily mislead us, we're all familiar with probably, is the optical illusion. This is my absolute favorite optical illusion in the whole world. Many of you may well have seen it already, but I can't resist it. And it relies on two patterns. We've got the pattern of a chessboard, and we've got the pattern of what things look like when there's a shadow. And Ed Edelman, who produced this, Edelson, was able to combine the two to do something rather bizarre. So there are two squares on that board labeled A and B, and they are actually both exactly the same shade of grey. Now, your brain does not allow you to see that. I've seen this picture thousands of times. I still cannot see them as the same shade of grey, but they are. I'm going to demonstrate that to you. I could be cheating even with this demonstration, but trust me, literally all I'm going to do is take the A and move it to the B. And when I do that, I'm not changing the colour of that A in any way. You will see they are exactly the same shade of grey. But because our brain understands the patterns of chessboards, understands the pattern of shadows and how they appear to work, it fools us. So we've all got to be very careful with patterns. Science is very careful, good science, about making sure it's the right pattern being applied in the right way. Another example of patterns going wrong is superstition. Superstition is essentially applying a pattern to an occurrence, but it's the wrong pattern. I suppose a classic example is our reaction to the number 13, the fear of 13, even has a fancy name. We're back to the Greek again, triskaidekaphobia. Nobody's really quite sure why the number 13 is associated with bad luck, certainly in Western parts. It's been said it might be something to do with the disciples in the Bible or whatever. I think it's much more likely, actually, that there was a pattern of events, a number of events came together when the number 13 linked them together, bad events, and people thought, ooh, it's something to do with that. But so strong is this that when people are designing things, they quite often actually try to avoid the number 13. You heard earlier on, I used to work in industry. It was most of my time was in airlines. And I went on a tour of Terminal 4 at Heathrow just before it opened up. And they showed us the gates at Terminal 4. Terminal 4 is a long, straight terminal. All the gates are in a straight line. And Gate 12 is at one end, or rather was at one end. Gate 14 is at the other end. And the reason they did that was quite simply so that people didn't notice there wasn't a Gate 13. Because if you notice there isn't Gate 13, you know Gate 14 is really the unlucky one because it's really 13. So they actually separated them so people wouldn't notice. Later on, people got so irritated by the fact they went to Gate 12 and then had to go to the other end to get to Gate 14 that they actually changed the numbering system. But they genuinely did set it up that way originally to try to avoid this. And superstition is a very natural thing. Even some birds appear to be superstitious, so that if they, say, do a particular thing and food appears, they will keep doing that thing on the superstitious assumption that doing that thing made the food appear. One last thing about false patterns before we move into the real thing. I mentioned earlier on that the number 13 might have been associated with a cluster of bad events. Clusters of events can be really misleading because we don't understand randomness very well. It doesn't come naturally to us as a pattern because it's a pattern with no pattern. And I think a good illustration of why this happens is to start off by thinking, imagine I've got a tin of ball bearings and I tip them on the floor. So I tip them on the beautiful wooden floor down there. And what would you think if the ball bearings landed on the floor like that? I suspect you would think something's odd. there are magnets under the floor or something, or it's Michael Faraday's ghost poking them, something is making them go into that shape. It's not natural. We would expect when you tip the ball bearings on the floor, they go all over the place. You'd have some gaps, you'd have some groupings of ball bearings, some clusters of ball bearings. And we can see that very naturally with ball bearings. But when we move out into the real world with all sorts of influences, this logic goes astray. So, for instance, if in the village 3 farmers' cows go ill, they used to blame the local witch. Nowadays, they're more likely to blame the phone mast or power lines. They don't incidentally tend to blame the local pub for some reason, even though there's probably one near as well. When we see a cluster of events from something that's random, we very naturally try to imagine there's a pattern. Of course, there are real clusters. There are real clusters, real in science, but it's not always the case. So as I go through the patterns tonight, just always bear in mind, these are our best understanding, our best patterns that we have applied so far. Some of them may change in the future, how we look at them. Science is never set in concrete. It is always evolving. So I'm going to start with my actual patterns by looking quickly at the cosmic microwave background radiation. For this one, we're going right back to the beginning of the universe. And in some ways, you can think of the cosmic microwave background radiation, which we'll see some illustrations of in a moment, as a fetal scan of the universe. It's a view of the universe when it was very young. And just like those ultrasound things you get when you're having a baby, it's pretty vague and fuzzy, but it gives us a picture of what happened early on. Now, in the very early days of the universe, it was opaque. Light couldn't get through it because there was too much electrical charge around and it just couldn't get anywhere. But about 375,000 years or so into the life of the universe, it became transparent. And at that point, the high-energy photons, the gamma rays, as we might call them now, could start moving around the universe. Since then, the universe has got bigger. It has expanded. And as it expands, what we have to bear in mind, the expansion of the universe is not a matter of something like, if I expand a book, a physical object, it's the actual space itself that is expanding. And because of that, if you think of light as waves, then you can imagine as the universe expands, those waves get stretched. Or if you think of light as photons, as I tend to more often, if you imagine a particle coming along and hitting something, it has a certain amount of energy. If the thing it hits is moving, it hits it with less energy. And essentially, as the universe expands, the energy of the photons drops. And what we have left is just very low energy microwave radiation. But it is all over the universe and has been traveling through the universe since 375,000 years in, 13.7 billion or so years ago. Now, the discovery of this was fortuitous and to some extent accidental. This is a device based in New Jersey at Bell Labs. It was originally constructed actually as a receiver and transmitter for communications. They were doing experimental communications. They're actually using reflective metallized balloons to bounce signals off to try long-range signaling that way. But it was realized with some of these early devices that they could also be used as radio telescopes. And a pair of physicists, Penzias and Wilson, were working with it at Bell Labs, trying to use it as a very early radio telescope. And they discovered there was a hiss, a microwave, very low microwave hiss, coming from all directions in the universe, apparently. Now, if you're working in a radio telescope and you discover a background hiss, your first assumption is that it's something local. I used to live near Jodrell Bank up in Cheshire, and when they first set up Jodrell Bank, which admittedly was before my time, but I've been told, they actually used to go around the houses and talk to people and try to either confiscate electrical equipment for them or at least fix it so it didn't produce static and interesting noises. The fact is you can get local stuff, and they looked into that and they managed to say, no, it's not about that. And the next thing they considered was a mysterious substance known as white dielectric material. Essentially what they discovered was a pair of pigeons were nesting in the horn. The pigeons were creating droppings, which were the way they rather coyly referred to them in their paper as white dielectric material. They thought that may possibly be causing the strange effect. So they scraped it all off, and the pigeons did it again. They then got quite inventive. They're working for Bell Labs. They actually put the pigeons in the internal mail and sent them to another bit of Bell Labs about 40 miles away. Unfortunately, they appear to have been homing pigeons, and they were back again by the next day. So I'm afraid, very sadly, they did become victims of science. They were actually shot. The white stuff was all, sorry, not my fault, I wasn't there. The white stuff was all cleared off, and it made no difference. I'm afraid they were martyrs unnecessarily. So it was discovered that this was something else, this was real. And as it happens, they had no real idea what it was. They talked to somebody else who just talked to somebody else. And in those days, no internet, no way things spread very easily. But luckily, they happened to phone the right guy who'd just spoken to somebody else about a theory that there ought to be this microwave background radiation flying through the universe at a particular level that was just right energy for this microwave radiation. And what I've called it there the sound. It's not really the sound of the universe because it's light, but it feels a bit like almost that they were listening to the sound, like the ultrasound with a baby scan of a new universe. All they could see really was something totally uniform. And it's taken a series of satellites to actually get more information on this. The first of those, COBE, was sent up in the 1980s. Should have gone a bit earlier because it was when NASA was still sending up satellites using shuttles. And unfortunately, the shuttle disaster meant it had to be put off. But the COBE satellite got up there. And what it was able to do is basically look in every direction and produce a projection of the whole universe in every direction. So just as, if you look at a world map, it's a flat projection of the spherical Earth. This is kind of an inverse version of that, and the kind of ovals we'll see in a moment are basically a projection of the whole 360 degrees everywhere around us view of the universe. Bearing in mind it was originally discovered as a uniform hiss, the very essence of the cosmic microwave background is it's pretty much the same everywhere. And in fact, the differences in it are just 1 in 100,000. The differences between the highest energy bits and the lowest energy bits are just 1 in 100,000. And everything you will see when you look at these maps of the output of these satellites is just trying to pick out that 1 in 100,000 difference, just to emphasize how difficult this was for the people doing it. In fact, it was so difficult the very first time they published a diagram. Unfortunately, it turned out the diagram was actually what they were publishing, a map of some problems with the microwave detector. There were just little local temperature variations, and that was what produced the original map. But thankfully, they got over that pretty quickly. And what they ended up with was this map from the light that set out 13.7 billion years ago. Now, the earliest images from COBE looked a bit like this. This is combining two frequencies, but it's not really a very useful map because when you're dealing with something as sophisticated as this, complicated as this, you've got to get rid of things that get in the way. So the data actually has to be processed very heavily. And bear in mind what I said earlier on about patterns. We think this is right, what they're doing is right, but it's just possible. It's not. Science is like that. But what they had to do, first of all, was take out some variations that were called by movement, expansion of the universe, movement within the universe. And it looked a bit more like that, but there's still this rather bizarre solid bar, which we didn't really expect across the middle of the universe. And that actually is down to radiation coming specifically from the Milky Way, which, of course, is in the plane. And that was what they ended up with. So a picture of variation between, if you like, the hottest and coldest bits, but remember, 1 in 100,000 from the hottest to the coldest in terms of the energy of these microwaves. What you can derive from that really needed a bit more. And there have been 2 more satellites since that have produced a lot more detail. The first was this Wilkinson one back in the early 2000s. One of the biggest things they did, apart from having a more sensitive detector here, is they moved it. The original one, you normally think of a satellite going around the Earth, and the original one did that. COBE did that. For this one, they actually moved it to a Lagrangian. So basically these points around the Earth where the gravitational pull of the sun and the Earth balance out. And you can orbit that just as if you were orbiting a planet, with the advantage is there's nothing there So instead of having this dirty grey planet in the way that makes it very slow to get a picture of the whole universe, you can actually see the vast majority of the universe at one go as you turn around. So they managed to do it from there, got a significantly better view, but it was actually very quickly replaced and improved on by a European Space Agency satellite, Planck, which was able to produce a lot more detail, and now you would see maps looking a bit more like this. I mean, there was the whole sort of egg shape. I've just cut that off for art's sake. So what we're seeing again is variation there. And in some ways, what's more important than the pretty picture, although the picture obviously is very interesting for us who are not mathematically analyzing it, is the vast amount of data that lies behind that image. So does it do anything other than give us a pretty picture? I mean, it's nice to know that we're seeing this stuff from 13.7 billion years ago. It started off then. But is it actually useful? Some people certainly think it's amazing. Stephen Hawking said this about it. Frankly, with due respect, I think that is hyperbole. I think it is interesting, and it does give us some information, although there's certainly doubt in there. But I'm not convinced it is the greatest discovery of all time. I think a better picture of it, another sadly deceased physicist, Steven Weinberg, who won the Nobel Prize in physics, was to say this, that actually in some ways, one of the really important thing about it is that it really pins down the Big Bang. It is such strong evidence in terms of where we've come from that we didn't have before. And there are a few specifics that have come out of that. So a picture, I guess, of the broad distribution of early matter in the universe. You could argue that you're starting to see seeds of galaxies starting to form, although it's questionable exactly how much detail there is there. It does suggest to us, or rather to the theoretical physicists, that dark energy, this thing that is accelerating the expansion of the universe, has been consistent over time, something that certainly isn't definite, but this gives us a suggestion in that direction. It also gave the suggestion that dark matter, or the gravitational effect that's attributed to dark matter, the existence of dark matter is yet to be proved, has about 5 times the gravitational impact of that of matter, and correlates with other evidence to that effect. And it did have a small change on the estimated age of the universe as well. But I do have to come back to this aspect of scientific patterns. This is a fairly easy pattern to misinterpret. There's dust in space, there's all sorts of stuff in space that can lead to misunderstandings, and it has with other experiments. So far, we're fairly sure that this is the good evidence, but the great thing about science is we will continue getting more data and get more certainty, or head off in a new direction. Now, this is a pattern, obviously, about something very big, the whole universe. For my second pattern that I want to move on to, we're going to look at something very small, specifically quantum particles, things like electrons, photons of light. And Feynman diagrams are used in something called QED, which, as Richard Feynman said, is a rather clumsy name. A short name, a rather clumsy name, quantum electrodynamics, which is the study of the interaction of light and matter at the level of quantum particles. This theory was developed independently by Feynman and also Julian Schwinger and Sinnatiro Tominaga. They won the 65 Nobel Prize for doing so. And from the sort of very general viewpoint, what it tells us is quantum particles don't behave like tiny tennis balls. If somebody talks to you about a particle, it's easy to think of it as something being little like a ball. If I bounce it off something, it bounces off like you would expect a ball to do that. But the fact is, actually, quantum particles are not that helpful. They actually do not travel in a straight line from A to B. If they get from A to B, all we know is there are probabilities of them taking every possible route they could possibly go on from A to B. Now, as it happens, those probabilities tend to cancel out in such a way that it mostly looks like they are doing a straight line, but those probabilities are real. And I think a good example of this, a simple one, you can actually try this at home, is the reflection of light. We're all taught at school, or certainly we were in my day, I don't know if it's more subtle now, that when you reflect light off a mirror, the angle it goes in at is the same as the angle that it reflects off at. And in fact, if you add up all these probabilities for an ordinary mirror, that is what's going to happen. But all those other probabilities do exist. And if you take your mirror and cut out some bits of that mirror, what you'll find is it no longer reflects at the same angle. Because the different probabilities that are being involved have been changed, and the result is it will reflect overall at a different angle to the expected one. This genuinely works. You may not want to take a mirror and carve bits out of it to do the experiment, but thankfully you don't have to, assuming your household is old-fashioned enough to still have a CD or a DVD, that's all you need. Because if you look at the back of a CD or DVD, what you've got is a reflective piece of material, a mirror, if you like, that has bits cut out of it. Those bits cut out of it are how it stores data, how data is stored on it. And because of those bits stored out of it, it starts doing this weird quantum reflection. Now, one effect that's involved here is it depends on the energy of the photons, the angle that the reflection ends up as. So different colors reflect at different angles. And because of that, when you look at the reflection of light from the back of a CD or a DVD, you'll see all those pretty colors. And that is this quantum effect in action. You can actually just do that experiment at home. Now, quantum electrodynamics gives us a pattern for understanding what's happening with this kind of quantum effect, and practically everything that involves electrons and photons, all our modern electronics pretty much is dependent on it. And what Feynman diagrams are a visual pattern that helps us both to understand and make calculations based on what's happening with these different quantum particles. I want you to imagine a very simple picture. We've got two electrons starting at A and B, and they end up at C and D. Now, one obvious way they can get from A and B to C and D is just like your good old tennis ball, straight line from A to B. And that is a perfectly reasonable possibility as one Feynman diagram for that process. But equally, they might have crossed over. So A might have ended up as D. We can't tell the difference between electrons. They are identical. There is no way of labeling an electron. So we don't know which electron ended up where. That is also possible. But for that matter, something more subtle can happen because electrons can give off and receive photons, light, particles. And what we've got here is they are sharing a photon in the middle. That, as a result of doing that, their energies change, their directions change. And so, although they wouldn't have ended up at C and D, they now did as a result of exchanging that photon. And you can do that in all sorts of ways. So what you do with Feynman diagrams is basically start to build up a collection of patterns that show you the way that it might happen. And they're very useful to understand what's possible, what may be happening. But as I say, they can also be used by associated numbers with them to do calculations. By the time you get to a slightly more complicated version, this is yet another level of detail, if you like, where the pair of photons being exchanged. You can get more and more of these. In fact, technically speaking, there should be an infinite set of possibilities. Obviously, to do the calculation, you're not going to do the whole infinite set, and you don't need to. By the time you just get, in this particular example, you get down to that fifth diagram there, that's only about 1 in 10,000 of the contribution to what finally actually happens. So you don't need to do that many to get a good approximation. QED often involves approximations when you're doing the calculations. But I think from our viewpoint, to some extent, the importance of these patterns is just seeing what's happening, getting a feel for what's happening. I just want to show one other interaction between electrons and photons, again showing the kind of things that these Feynman diagrams can deliver to us. So here we've got coming in from the bottom left an electron. It absorbs a photon, goes up in energy, that changes its direction. A bit later, it gives off a photon, changes direction again. This is a process called scattering. Scattering, for instance, is how you end up with the blue sky and so forth, that the light gets scattered in this kind of way. But that's not the only way it can happen. In this example, the electron actually gives off a photon early on, drops in energy, and then absorbs the photon later on and goes up in energy. And here's a third example where things get positively weird. Quantum physics is often described as weird. I don't think it really is. I like quantum physics. I think it's fairly straightforward if you can get your head around probabilities instead of everything being fixed and solid. But sometimes it does feel a bit weird, and this is a good example. So one way of describing what's happening here is an electron is coming in from the bottom left. It gives off a photon, travels backwards in time, absorbs another photon, and then travels forward in time. Because bear in mind, time is the vertical axis, and it's actually coming backwards in time. This is perfectly possible as far as quantum physics is concerned. There's nothing that prevents this happening. However, there is another way of describing what's happening here that most of us feel a little bit more comfortable with. And that's, instead of starting with the electron in the bottom left, let's start with the photon in the bottom right. So what we've got here is a photon coming up from the bottom right. Now, Einstein equals mc squared tells us energy, matter, interchangeable. Light can actually generate matter. Matter can result in energy. And what's happening here is that photon is so energetic, it actually produces a pair of particles, one going off to the left, one going off to the right. The one going off to the left is what's called an antiparticle. It's antimatter. In this case, it's a positron, an antimatter electron. When light produces matter, it usually produces antimatter and matter imbalance. Now, interestingly, in a Feynman diagram, a normal piece of matter going backwards in time is the same as a piece of antimatter going forwards in time. So rather than thinking of it as an electron going backwards in time, even though there's a perfectly reasonable way of thinking of it, it perhaps is easier to think that's actually a positron that's been, antimatter electron that's been produced, going off to the left. That then collides with an electron. When an electron and a positron, matter and antimatter collide, they produce energy, so you end up with a photon heading off. So two different ways of looking at it. And again, the Feynman diagram, I think, helps us explore the physics, get a feel for what's happening in a way that wasn't possible when all you had was a set of formulae and numbers. These things have been extended. They've been extended to include something called quantum chromodynamics, which is where you bring in quarks, the subatomic particles that make up neutrons and protons, for example, and the gluons that are used to, if you like, to stick them together. These are much more complicated in the way they interact than just electrons and photons, say, and as a result of that, you do get an awful lot of possible Feynman diagrams if you want to describe QCD properly. There is a hint of a way of getting around this. There's something called an amplituhedron, which is based on a slightly weird bit of mathematics, sort of multidimensional mathematics, something called a positive Grassmannian. And it seems to be a way of combining many different calculations into a single relatively simple structure. And they have done that once or twice in a sort of reverse engineered way. What they don't know yet is how to go from a particular situation of particles and produce the right amplituhedron. So whether or not this will ever be useful, we're not sure, but it seems to be a way of extending the concept of Feynman diagrams to the next dimension. We'll just have to watch how that's developed. So what we're doing with Feynman diagrams is visualizing, calculating the impact of quantum interactions. The next pattern I want to look at is also about the impact of interactions, but in this case, we're talking about atomic structure. And it's probably a much more familiar one in that it's very difficult to go into any science lab at school or whatever without seeing a periodic table. And what we're looking for, what the scientists who developed the periodic table were looking for, were patterns in the behavior of the elements and what would eventually be seen as the atoms making up those elements. It really started, probably you could say, with John Dalton, working in Manchester, the start of the 19th century, who produced this early table of elements. The structure here, the pattern he was looking for was relative weights. So he gave a weight of 1 to hydrogen and other weights to various other elements. He got a lot wrong. Most of his weights are wrong. Some of the things he put down as elements are actually not elements. However, you have to bear in mind, he was working with equipment that was really bad by the standards of the time, and all the equipment at the time was really bad. So the fact is, that he did this at all was quite amazing, and he gave a first thought a little bit of idea of structure based on weight. After his work, various scientists across Europe started to look for different patterns in elements. One example was a guy called Dobereiner, and he thought that elements behaved as triads, so collections of 3 elements that could be combined, if you like, because they had similar behaviours. So 2 good examples, lithium, sodium, and potassium, chlorine, bromine, and iodine, react in quite similar ways. But unfortunately, he found he couldn't apply these triads widely across the known elements. There were various other attempts to put together some kind of pattern, some kind of structure. They were starting to get an idea of valence, so the idea that different elements combine in different numerical ways. So you think, for instance, of carbon and hydrogen, your basic molecule, methane, of carbon and hydrogen, 1 carbon, 4 hydrogen. So if you say hydrogen has a valence of 1, carbon has a valence of 4, you can stick 4 of the hydrogens onto the carbon. So this was looking at structure based on how atoms interacted. But all this really led up to the development by Dmitry Mendeleev in 1869 of the very first modern-style periodic table. I said modern style, it's modern style-ish. It was just in writing, there were no pretty pictures, and also it was actually at 90 degrees to the direction we now see the periodic table in the form you probably will typically see it on the wall in your science lab. This is just a slightly prettier version than some because it actually includes the maximum valence of each of the elements. Now, what Mendeleev was able to do from his pattern, he obviously didn't have all this. These are the whole 118 elements that we now recognize. He didn't have that anywhere near that number. And even if you look at the relatively well-known ones, there were some gaps. So if I just block off 4 there, these were 4 elements that weren't known to exist. And Mendeleev said they did exist. He predicted their existence based on the pattern. He called them Eka, followed by the name of the element immediately above them. So the one under silicon, for instance, was Eka silicon. Eka Sanskrit, I think it's like 1, so it's like 1 up from that. Eka silicon, now germanium. And he was able to predict quite a lot of its properties quite accurately. He didn't get all of them really well, but he got germanium particularly well in making that prediction. Over time, obviously, we've added elements, both in terms of finding them and then producing them. Ones that aren't natural, the natural ones go up to about 92 on the Earth, 94 in the universe, and the rest are all artificial, up to 118. 118 is the most recent one, Arganeson, and I pulled that up really to show the underlying pattern, the pattern that produces the pattern of the periodic table, and that's down to the structure of the atom. Now this looks like the dots around the edges are electrons. It looks like the electrons are kind of going around orbits like little moons. It's not like that. They do not go around orbits. We're talking quantum particles. Remember what I said before, it's all probability. They're all fuzzy clouds of probability. But the fact is they do form kind of shells of different levels of energy. These build up as you go through the elements, and it's the outer shell that determines how the elements will interact with each other and determine the position of the elements in the periodic table in terms of the first level, the sort of one, the 8 level. The outer shell pretty well always goes up to 8. Then you get an extra shell, and that outer shell can have more in it if it's one of the outer ones, confusingly, which is why it's such a weird shape. But it's down to, well, the table's such a weird shape, but it's down to the building up of that structure of the atom that we get that periodic table. You can do it different ways. So this version of it, instead of having the 2 long bits in the middle taken out, which we almost always do just to avoid it being too long, this has put them actually in place. The reason it does this is just to show another pattern in the elements, which is metals and non-metals, one of the other things you can see in the periodic table. So basically all the ones that are turquoise are metals, the majority of elements are metals. Right up in the top right, you've got a triangle plus hydrogen over the other side that are non-metals. And then the really interesting ones are the pink ones on the diagonal, which are semiconductors. Those are the ones that give us all our wonders of electronics, is making use of those semiconductors. The dark ones at the bottom, incidentally, are artificial elements that we've made so little of, we actually don't know what their properties are. We can guess what they might be, but 1 or 2 have already proven not to be quite what they seem. So they tend to be left in isolation. I think one of the most fun aspects of a pattern in terms of the elements is the naming of the elements, actually, because it's not been down to your standard scientific, let's plan everything out nicely approach, because it's happened over such a long time. There's a whole range of ways that the pattern of the elements' names come in. Sorry, this writing is a bit on the small side because there's so many to get through. Some of them are golden oldies, so ones that came up before modern science, so things like iron or tin or sulfur, elements we were aware of before we were aware there were elements, really. And often those names come from classical sources, particularly the symbols used to represent them on the periodic table. So, like Fe for iron because it's from ferrum, so forth. They're all Latin, actually, except for that last one. For mercury, it is actually a Latinized version, but it's a Latinized version of a Greek name for the Hg for mercury. Then you get into the more early scientific stuff. One or two of these are from how we got the elements in the first place. So fluorine is actually named after the mineral fluorite, which itself comes from the Latin fluere, which means to flow because it was used as flux in smelting iron. So that one came, from the mineral. Several of them have actually, but others are down to their properties. So there's some that are related to color. So we've got green for chlorine. We've got violet for iodine. Iridium, of course, is iridescent. We've got smelly ones like bromine and osmium. So some to their properties. And some were just trendy at the time. Genuinely, it was just, that's interesting, let's call it that. A bit like calling it, after the latest celebrity or whatever. In this case, in the case of palladium, the asteroid Pallas had just been named, Pallas being named after the goddess Pallas Athene, and they thought, that's a nice name, so we'll call our new element Palladium after that, not after the well-known theatre in London. Other ones, though, are named after places, some of them fairly obvious, although funnily enough, germanium was named that before Germany was called Germany, but it was discovered in Germany. It was an ancient name for a region of there. So we've got Scandinavia there, we've got Poland, we've got this little collection all from ores that were found near the Swedish village of Ytterby, so yttrium, terbium, erbium, and ytterbium. And I think the best one of all, thulium, which was a total error on the part of the person who named it. He wanted another one to name after Scandinavia. So he thought, I've heard of this ancient name for Scandinavia called Thule or Thule, as he pronounced it. And unfortunately, it wasn't that at all. It was actually the name of a mythical place north of Great Britain. It wasn't Scandinavia at all, but he got it wrong. But hey, that's what he called it. We get then more pinned down, if you like, locations where the element was first discovered. Quite a lot of American ones there, obviously, americium, berkelium for the University of California at Berkeley, californium. You've then got ones for the Lawrence Livermore Laboratory, a couple there, darmstadtium and nihonium for Japan. And finally, we see elements named after people. Two really interesting ones. These two are actually named after discoverers of elements. Glenn Seaborg discovered many of the lighter artificial elements, so the ones that come out just after uranium. And Yuri Oganessian discovered some of the really heavy modern ones. He's the only person, incidentally, that's had an element named after him while he's still alive. As opposed to this group, who had nothing to do with the discovery elements, but were thought to be famous enough that it's worth calling an element after them. I think we're just waiting for Faradayum, actually. We haven't got that one yet. I ought to finally say, when we're thinking of the periodic table, that the form we normally think of it in, with those interesting tiles as featured in Breaking Bad, is not the only way of representing it. There are many, many ways of representing the periodic table. This is a periodic table. I think this is one of the most beautiful ones. It's functionally not very useful, actually, but it does look really nice. And there are all sorts of different ways of doing it, but we always tend to come back to some variant, actually, of the traditional one, because actually it is quite useful to have it in that form. Just finish off on the periodic table there with a quote from Neil deGrasse Tyson, partly because it's a rather pretty quote, in saying, a zoo of one-of-a-kind animals conceived by Dr. Seuss, but also actually because it's so wrong, because the whole point of the periodic table is it's not one-off. these things actually have relationships. They have a pattern. It's about a pattern. And a zoo of one-off things is not a pattern. So I'm sorry, Neil, you got that one wrong. But it's rather a nice description even so. Let me move on again then to a totally different kind of pattern, the number line. Very basic in some ways. It's the pattern that underlies arithmetic. It's something your children are probably taught in school if you have children. If you're as old as me, I don't think we were taught it in school, but we certainly had rulers, and it's a bit like basically a ruler that goes off to infinity with all the numbers on it. And you can see how the number line underlies arithmetic with a very simple real-world arithmetic operation. If I have 9 apples, and somebody gives me 5, I can take 5 steps up the number line and find out how many apples I've now got. I've got 14 apples. The real number line actually, of course, goes both directions from 0, whereas physical objects, it's a bit harder. I can't actually be given -5 apples, although somebody can take 5 away. But the number line is effectively going off to infinity in both directions and underlies all of arithmetic. It's a pattern in itself, but it's a pattern that's based on patterns, specifically patterns called sets. Which are very important in mathematics, specifically in the basis of arithmetic. And in the end, mathematicians sometimes sneer a bit about arithmetic. It's not really very interesting, but it's actually the stuff we use a lot, most of us, when it comes to maths. Sets are actually very general things. You can have a set of everything that's coloured orange. You can have a set of the things you saw this morning. But in maths, obviously, we tend to deal with sets of numbers, and the patterns there are often in terms of how those numbers are related. So you might see the set of the natural numbers, which are the real whole numbers, so 1, 2, 3, 4, 5, all the way up towards infinity, or the prime numbers, the numbers that can only be divided by themselves, or 1, except for 1. Another thing that's escaped from the pattern of sets is the term subset. We use subset quite a lot in the ordinary world, but it is a mathematical term, and it refers to a set that is a part of another set. So for instance, the even natural numbers are a subset of the natural numbers because there are also the odd numbers in there. Natural numbers themselves are a subset of the integers, which go negative as well as positive, and so on. Now, when set theory is used as the basis for arithmetic, it starts off in a really interesting way where you start off with the set that has nothing in it. It's called the empty set, and 0 is defined as being the empty set. Then for 1, the little curly brackets basically just means a set containing. So number 1 is a set containing the empty set. Number 2 is a set that contains the empty set and the set containing the empty set, and so on. And it builds up like a set of Matryoshka dolls, that it gets sort of bigger and bigger. And that's the underlying definition, as far as mathematics is concerned, of number. So it's the underlying pattern of number. And one thing that's really important with sets is their cardinality. I'm going into this thing about sets because I'm going to come back to the number line at the end, but I want you to understand one thing, this aspect of cardinality, to see something really weird about the number line. If you think it's a simple pattern that's just for primary school children, I want to show you it is actually a really weird pattern. But for that, we do need to understand this concept of cardinality. Cardinality is just the measure of the size of a set. It's how big it is. So to give a very simple example, imagine I've got 2 sets, the set of legs on my dog and the set of the horsemen of the apocalypse. I compare off the legs on my dog with the horsemen of the apocalypse. And at the end of that, there's 1 of each for each. It's a 1-to-1 correspondence, and that means they have the same cardinality. And I can do that even if I don't know how many legs there are. There are 4, but I don't need to know that. If I compare them off 1 by 1, 1-to-1 correspondence, they have the same cardinality. The sets are the same size. This is really important once we get onto infinite sets, which, remember, if we're dealing with the number line, it goes on forever. So the numbers in the number line are infinite. Now, infinite sets are weird. They're just like the quantum theory of sets, because what we find is you can put all sorts of infinite sets in a 1-to-1 correspondence, so they have the same cardinality. Here's one example that actually Galileo pointed this one out, that you can put the natural numbers, the positive integers, in a 1-to-1 correspondence with the squares. Each number has a square, so there's a square for each number. They have a 1-to-1 correspondence. Even though there are many more natural numbers than there are squares, they have the same cardinality. And in fact, almost a definition of an infinite set is you can always put it in a 1-to-1 correspondence. It will always have the same cardinality as at least one subset of itself. So that's slightly weird. And a German mathematician called George Cantor worked on set theory, developed a lot of set theory, but also was very interested in these infinite sets and their cardinality. And he did a lot of work on comparing the size of infinite sets. And we're nearly back to the number line, but we need to see one more thing that Cantor did. Specifically, he asked what was the cardinality of the set of the rational fractions. So that's every fraction that's a whole number divided by another whole number. So imagine this is a table of every single rational fraction. So it's going off to infinity that way, down to infinity that way. We've got every single rational fraction in. Now it's natural to feel it's bigger than the set of the whole numbers, but it's infinite. Can it really be bigger? And Cantor proved it wasn't bigger. And the way he did this proof essentially was to say, let's find a path that will take us through the whole table. Once you've identified a path, step by step, that will take you through the table, each of those steps can be put in one-to-one correspondence to one of the integers. It's the same cardinality, it's the same size. He happened to use that route. You could use a totally different route. It doesn't matter. As long as you can find a route through the table that you can do step by step in a systematic way, it has the same cardinality. So we now know that the integers, let's say the positive integers for simplicity, and the rational fractions have the same cardinality, they're the same size. So now let's go back to the number line for, I think, an absolutely amazing pattern. And it requires the use of one other infinite set. That's the set of fractions that go half, a quarter, an eighth, a 16th, and so on. So there are an infinite set of these. You can keep on doubling that forever. It's never going to come to an end. And what I'm going to do, because this set has the same cardinality as the rational fractions, is I'm going to pair off each rational fraction of the number line with an umbrella. And each umbrella is the size of one of these fractions. So just to give an example, here's a bit of the number line. I've randomly chosen the fraction 22 over 16, and I put an umbrella, this happens to be the biggest one, but it doesn't matter which one, the half umbrella. So it goes a quarter to one side, a quarter to the other side. It will always take you to another rational fraction. Now remember, I've got one of these umbrellas for every single rational fraction, so they're going to overlap. I can put an umbrella on every rational fraction, and they will overlap. So I can cover the entire number line with these rational fraction umbrellas. However, something quite interesting about that series, a half, a quarter, and an eighth, and a 16th. If you add that entire series together all the way to infinity, you just get one. So if you put all those umbrellas in a line, they're just one long, the entire set of umbrellas. But you can actually use them to cover the entire number line. And that's the sort of pattern that mathematicians love, because it totally puts your brain into a spin. Don't ask me afterwards, what's wrong with this picture? Because nobody really knows. But it really is just quite remarkable that as far as you can tell, you can put an umbrella on every fraction. It will cover to another fraction, cover the entire number line, but the only one in width. I'm conscious I'm getting towards the end of my time. I need to move on quickly to my last two patterns. I want to say a little bit about the DNA double helix, something I think most people will be familiar with. DNA stands for deoxyribonucleic acid. It's a compact name, just as, for instance, tryptophan synthase is actually this chemical. This is about the biggest one that has a full name. DNA typically is a lot bigger than that. But it's not actually a molecule. DNA is a family. It's a framework of patterns. And those patterns are found in chromosomes in living things. Each chromosome is just one molecule of DNA. The biggest one we have, human chromosome 1, 10 billion atoms in it. We're talking a seriously big atom. And the DNA we have in us is quite amazing. So each single cell in your body, apart from things like red blood cells, have a set of chromosomes in them. The chromosomes from one single cell are 3 meters long if you lie them all out together. But because we've got so many cells in our body, if you laid out all the chromosomes in your body, all the DNA, it would actually be about twice the diameter of the solar system. There's that much going on inside you. And each of those helixes, each of those DNA double spirals is a collection of information. It is a pattern. Now, we're familiar from computers with the pattern of bits. So something that can have a value 0 or 1, it's binary. But in DNA, we're dealing with quits, if you like, because it can have 4 separate values. They're usually given the letters C, G, A, T. Lots of you are probably familiar with this, which I want to go through it quite quickly, but I think it's interesting when you think of it as a pattern rather than think of it just as biology. So these letters, CJT, correspond to these four chemicals known as bases, and they form, if you like, the treads in the spiral staircase of the double helix, each one paired up. So you always get T with A, you always get C with G, or vice versa. So A with T, G with C. And because of that, you can split the helix down the middle, divide it into two, and the information in one side is reflected in the information on the other side. You can rebuild it. So when a cell splits, you can split and duplicate the DNA. That's why this pattern is so important. And what that gives us in those chromosomes is in many ways something that defines us as organisms. We have 46, 23 pairs, quite variable. Some ants only have 2 of them. Dogs have more than us. If you go up, kingfishers have significantly more. Some ferns actually have over 1,000 chromosomes, although to be fair, a lot of those are duplicates. Similarly, the information within the chromosome is measured in base pairs. And if you look at the whole collection, so base pairs are these pairs of the number of these pairs of chemicals, like the C and the G, the A and the T. You can range from bacteria, we're down to 100,000 base pairs up to a few million. We're around sort of middling mark, about 3 billion base pairs. And you can have some organisms, again, that have vast numbers more. But what's important to us, obviously, is the patterns within those base pairs. The thing we're most familiar with is genes. Genes are very common. A lot of them shared across a lot of organisms. So we share about 96% of our genes with chimpanzees, about 60% with bananas. And the main role really for them is to code for proteins. It tells the body how to produce complex chemicals called proteins that are many of the building blocks of life. I would say that it's variations in these patterns that are referred to as mutation. They're the way that, if you like, one of the ways that new species can evolve. But of course, the variations in us is partly because we get genes from both of our parents, so we're a mix of those. But it's worth also saying that the genes themselves are only a relatively small part of what's going on in the patterns in DNA. Now there's a big study of the rest, called epigenetics, the stuff that goes on outside the genes, and they have a huge role. Some people have described DNA as being a bit like a blueprint. It's not really that kind of pattern. It's more like the genes are like the specifications of the machinery to do stuff, and the epigenetic bits are a control program that switches bits off and on. So it switches genes on and off, makes things happen at the right time in the right place. So it's all important. It's not just about the genes. So it's a very quick whip through that, because hopefully you've covered it. Because I wanted just to get symmetry, and I'm conscious I really want to finish in about 5 minutes' time. But I would like to say a few things about symmetry, partly because as a pattern, it's something we're very familiar with. And yet, we tend to think of symmetry as being about art, but actually it's crucial to physics. It happens a lot in physics. It turns up a lot in physics, as we'll see. When people talk about symmetry, they often think about mirror symmetry. So basically one aspect of an image reflects the other side. When Pascal talked about symmetry, he was probably thinking of mirror symmetry when he said this. But actually, mirror symmetry isn't all of it, and it's not quite as simple as it seems. Because mirrors don't actually work the way we tend to think. If you look at that picture of somebody looking in a mirror, our natural inclination is to say that she's got her right hand in front of her face, the reflection has its left hand in front of its face. And so the mirror is swapping left and right. But the obvious question then is, why would the mirror swap left and right, but not top and bottom? And the answer is it doesn't. It doesn't swap left and right at all. And you can prove this to yourself at home, as I did here, by holding up a book or a magazine to a mirror. When I'm holding up my book there, I'm actually looking at the back of my book. But if you look at the picture, I'm not sure how clear it is there. Yeah, I think it's very clear. You can see the spine there at the right-hand side. So the mirror image is actually looking at the front of his book. It's got different text on it to mine, but he's looking at the front because the spine is on the left. I was looking at the back of mine in the real world. So what the mirror actually does is not reverse left and right. It's like almost taking a rubber mold and inverting it. It actually reverses front and back. So in a sense, mirror symmetry isn't actually what a mirror does, rather strangely. Now, mirror symmetry is something we find attractive. A lot of architecture uses it. For a long time, it was said that facial symmetry was important, that we actually like people more if they have symmetrical faces. And it was suggested this was because healthy people would have symmetrical faces, and in terms of natural selection, good to be healthy. Actually, unfortunately, quite a lot of research in the soft sciences, if you like, psychology and such, have proved to be a bit iffy, and this is one of them. It's not totally clear this is the case, actually, that we particularly attracted to facial symmetry. The original experiments were a bit dodgy. But even so, what is certainly true is symmetry is something visually that you will see in the vast majority of animals. So a bilateral symmetry down the middle, that the one side is pretty much a reflection of the other side, at least externally. Obviously, internally, if you get into internal organs, it's not like that. It's not true of all animals. But certainly, if you look at something like a tiger, and as Blake so nicely put it, it has that fearful symmetry in its appearance. But mirror symmetry isn't the only symmetry. I'm just going to point out a couple of other types. So you can also have rotational symmetry, where something looks the same when you rotate it. So if I take this image and rotate it by 60 degrees, or if you ignore the edges, I'm imagining it to go on forever, it basically looks the same. You can see that it's simpler with something like a square. If I rotate that through 90 degrees, it looks the same. Whereas if I did it at 45, it wouldn't. Now, it's true of a square, but if you move to a rectangle, 90 degrees doesn't cut it. You have to do a whole 120, not 90, to get back to it looking the same. I would say, by the way, things that are rotationally symmetric can also be mirror symmetric. So, for instance, you've got a mirror symmetry line down the middle and across the middle of this too, but it doesn't have to be the case. So if you look at something like this, it is actually rotationally symmetric. It has the pattern of rotational symmetry. It looks the same after I've rotated it 120 degrees, but it has not got mirror symmetry. Also true of the Isle of Man's three-legged thingy. Incidentally, there is another type of symmetry that's crept in there because the animation didn't quite work. It's actually moved sideways as well as rotating. Translational symmetry is when something looks the same when you move it sideways. And obviously, it doesn't on that screen, again, because the screen doesn't go on forever. But if this was an infinite space going forever, it would. And you see other types of translational symmetry happening in things like wallpaper, where you get actually 17 different possible types of translation, in tiling, and in nature, in crystals. So, for instance, of course, famously, a snow crystal, ice crystal, is six-sided symmetry because of the shape of water molecules. The reason symmetry has crept into science, physics specifically, is probably mostly because of mathematics, and particularly something called symmetry groups. And remember I mentioned sets earlier on. A group is basically a set where you can take two bits of the set, two elements that are of the set, and produce a third one by doing an operation. So for instance, the integers, if you take two integers and add them, you always produce another integer. So that is a group. And symmetry groups are groups of rotations. So one example, for example, the tetrahedron, the three-dimensional shape of tetrahedron, has this symmetry group because there are these different ways you can rotate it and produce the same thing. If you go to something more complex in shape, the symmetry groups can get quite big. So the estimate for the size of a Rubik's Cube symmetry group is that number, which I won't even attempt to read out. So just to finish off, the reason symmetry has become important in physics started around the start of the 20th century with a German mathematician called Emmy Noether, and she proved that the conservation laws, so things like conservation of energy, are linked to a form of symmetry. Specifically, if something slightly obscure, I won't go into any detail now, but called the action. So, for instance, if you throw a ball, the action of that ball is the difference between its potential energy and its kinetic energy as it moves, and the way it moves is defined by keeping that to a minimum. If that thing, that action, is conserved when you have some symmetry operation, then you get a conservation law out of it. So, for instance, if actions are the same later on in time as they were earlier in time, so a change in time doesn't affect them, you get the conservation of energy. If you move them from one part of the universe to another part of the universe and it still works the same way, then there has to be conservation of momentum, and so on. All the conservation laws can actually be derived from symmetry. This is fairly heavy-duty mathematics, but it can be done. And symmetry has gone on to be used, for instance, to predict the existence of quarks, of these subatomic particles, from a symmetry group. And also symmetry breaking, the breaking of symmetry, has become important as a pattern in understanding how, for instance, the way the forces of nature evolved over time. Each of those, frankly, is a book in its own right, so I'm not going to try to go into any detail, but symmetry has become really important to physics. So to finish off, patterns are absolutely central to our understanding of the world, but particularly to science. Famously, the poet Keats accused Newton of unweaving the rainbow, of making the rainbow boring and unbeautiful by looking at the science of it. But I think actually what patterns do is not only give us the beauty, but also the ability to look under that, see what's happening, understand what's happening. And I think that's better, to go from that surface beauty to the deeper understanding that patterns give us. As I mentioned, there is a book covering this, which I think I might be signing afterwards. I also want to mention, incidentally, due to the oddities of the COVID pandemic, I actually had 2 books that came out at the same time. So I think we do have copies of the other one as well. And I'm trying to basically corner the market on books with 10 in the title. So just to mention that there is that other book out there that's basically about 10 key moments in history of physics that have produced things that actually changed our everyday lives. Those books will be out there, but what I've been trying to cover today is just an overview of the importance of patterns and how they influence the world around us, how they can help us understand and explain the universe. I hope that's been interesting. I'm sorry I've cut into the question time, but I hope you've found that useful. Thank you very much.